This is the cytoskeleton, microtubules, dynamic instability. Dynamic instability is a process which specifically describes microtubules, so you should definitely associate dynamic instability with microtubules only. And this is the switching back and forth between polymerization and depolymerization of the same microtubule. And basically the idea is that each microtubule is independent of the other ones, especially if we look at, say, the centrosome, some sort of MTOC over here. Each of these microtubules is doing their own thing. I put this little saying like you do you, so each of them is just on their own journey about if they are growing or shrinking. They may collapse all the way back here and then start to regrow, or they may just keep on growing. They might grow partway and then collapse and then grow back further and so on. This allows for rapid remodeling of the microtubules. And remember that the dynamic is a take-home message for this whole section about the cytoskeleton. And it's a very big theme for cell biology overall. I'm going to put a little symbol for a little house here to remind you about those take-home messages, which they are up on Moodle and I mentioned in an earlier video. So here's an analogy about what the centrosome is. So the centrosome is basically like a fisherman. And so the microtubule that is growing is like the line that the fisherman is casting out. And so the idea is that at each location here, maybe say at the gamma tubulin ring complex, the microtubule can grow and shrink. And basically, when a fisherman is fishing, sometimes they cast and hit something right away, and then that will stick, if you will, and there'll be a long interaction with this line. Other times, they might throw that out, and it might not get to the right spot, or just not be a good cast, and then it'll be retracted, and the fisherman will reel back in that line, and then build it again. And that's basically what might happen here if they're retracting. The big idea is that the process of building these arrays of microtubules is due to random exploration and selective stabilization. And then this can lead to an organized array of microtubules that's reflective of the cell's needs at any particular time. So like over here. And one of the things that cells use the microtubules for from the MTOCs is to position organelles. I also want to point out there's a really great movie on the website. This slide features figure 17-13 from your textbook. Now we're going to check out figure 17-14 from your textbook and in particular highlight the microtubule capping proteins. Your book doesn't do a great job of defining what these are, although they do define microtubule associated proteins, and these are one example of a microtubule associated protein. The microtubule capping proteins are shown in red, so each of these little circles is a microtubule capping protein, and each of them is bound to the cell cortex. Each of these can bind to the plus end of a microtubule as it reaches to this location, and then it can stabilize it. And so in this picture you can see that from the centrosome there are lots of microtubules that are reaching out, again in a random array, and then some of them are going to continue to go outwards. As you can see with this arrowhead, some of them are going to start to shrink back. The ones, for example, it looks like maybe one of these guys over here, eventually if they bump into one of these microtubule capping proteins, then they're basically locked in place and stabilized. On the other hand, all these other ones are still going through dynamic instability of growing and shrinking, but this is going to be a stable connection. And then notice that here's another one. If this guy bumps into a microtubule capping protein, now that one also gets locked in and stabilized. Remember that the minus end is attached to the gamma tubulin ring complexes, so those are stable, and that the plus end is the end that is typically unstable. Going back to our fishing analogy, this centrosome, realistically, there's a whole bunch of fishermen. Each of these microtubules that is reaching out is a different line, and each of those is independent. Oh, and it looks like somebody got one here. So why this is important for a cell overall is that this locking in, if you will, or stabilization of certain microtubules can polarize the cell. And notice that the cell starts off with this very round structure and then starts to get a little bit elongated over here. So this might lead to the cell changing shape, and this would, of course, be using other parts of the cytoskeleton as well, but this is going to help provide some of the structure for that. The last panel of this figure from your textbook is not shown on my image here, so I just kind of drew it in. Basically, notice that the cell has continued to change shape and basically to have this two different sides. So remember that the polarity is indicating that we've got certain things on one side of the cell and other things over here. And so one of the big things that can be polarized is the location of organelles or other vesicles. When we talk about that polarity, it can mean a number of things, one of which is it could refer to the shape of the cell, also unequal distribution or orientation of proteins. For example, the plus ends of the microtubules will be over here and minus ends are over here, so that's a polarity for this cell, in addition to its shape. And any organelles that might move along these microtubules also would lead to a different distribution. And so polarity, of course, we know for the North Pole, the South Pole of the globe, and then in other parts of organisms, for example, head versus tail, back versus belly. Different sides are key for distinguishing function. I also wanted to pimp out the inner life of the cell and give you some specific time points to refer to look at microtubule dynamics.